Okay, calculus, let's do the magnitude of t prime of t. I know when I do all these denominators and I square them, I should have a t squared plus 2 to the 4th. That'll pop out of the square root, so this should be t squared plus 2 squared popping out of the square root, because they're all the same. So when I square them and take the square root, we should be fine. But I'm going to have a 16t squared. When I square this, this is a binomial, so that would be 4t to the 4th. Looks like minus 16t squared plus 16. We have another plus 16t squared. Now, a 16t squared is going to cancel. This is 4t to the 4th plus 16t squared plus 16. I can pull 4 out, so it would be 2 times the square root of t to the 4th plus 4t squared plus 4. This is a perfect square. It's t squared plus 2 squared. So this is 2 times t squared plus 2 over t squared plus 2 squared, which is a nice, one of them will cancel. So this is 2 over t squared plus 2. So that is t prime of t. That's the magnitude of it. And we know it's divided by the magnitude of r prime of t. So if I take this and divide by another t squared plus 2, k in total is 2 over t squared plus 2 squared. So it could have been ugly. Didn't end up nearly as ugly as I thought it was going to be. Sometimes we get small victories in life. Okay, so how can we do curvature in rectangular coordinates? Let's see. Theorem 12.9, curvature in rectangular coordinates. If C is a graph of a twice differentiable function given by y equals f of x, the curvature at point xy, k equals, it looks like the absolute value of y double prime divided by 1 plus y prime squared, quantity to the 3/2 power. The circle of curvature gives you a nice way to estimate the curvature k at point P on a curve graphically. Using a compass, you can sketch a circle that lies against the concave side. Point P, if the circle has a radius r, then you can estimate the curvature to be 1 over r. So find the curvature of the parabola defined by y equals x minus 1/4 x squared at x equals 2 and sketch a circle of curvature roughly at the point. We're just going to go one thing at a time. So let's find the curvature. So we know we have the formula from above, k equals the absolute value of y double prime. Let's take the derivative and second derivative of y. That'd be 1 minus 1/2 x. The derivative of that should be negative 1/2. So if we take the absolute value of negative 1/2, it would be 1/2 over 1 plus 1 minus 1/2 x squared, quantity to the 3/2. So let's see how this math unfolds in the denominator. Still 1/2. I'm going to expand here. That's 1 plus 1 should be minus x plus 1/4 x squared to the 3/2. Which means k is 1/2. This is now 2 in the denominator. 2 minus x plus 1/4 x squared to the 3/2. Now it wants it at x equals 2. So this would be unpleasant to expand further, but we can plug 2 in. 1/2 over 2 minus 2 plus 1/4 times 2 squared, all to the 3/2. Now something nice happens here. These cancel. 2 squared is 4. 4 times 1/4 is 1. So this whole thing is 1 to the 3/2. So k is just 1/2 at x equals 2. So generally speaking, if k is 1/2, we know k is 1 over r, which means r is 2. So there should be a circle of radius 2. So if we draw this parabola, We know we're at the point 2, 1. And if we draw this parabola, it goes through the 0, 0. Also goes through on the other side 4, 0. So it makes a rough shape like this. Over 2, down 3, over 2, down 5. I'm just sketching the graph, and by sketching I mean I'm algebraing the graph so I can get the graph. So what does this mean? This is the shape of our graph. What is it talking about our circle of curvature? Well, it's a circle of radius 2 that touches 2, 1. That's like inside the graph. So we go towards the concave side of the graph, radius 2, which means down 2. And that means we draw a circle of radius 2 that roughly represents what this thing looks like. Let me find a color. So if I go 2 out from the point 2 below this, it's a circle that it rubs up against the parabola basically and kind of shows the curvature. It's very similar curvature to what the parabola is actually doing. So that's all it really is. So let's move to the next page. Okay, so we've got acceleration, speed, and curvature. If r of t is the position vector for a smooth curved C, then the acceleration vector is given by a of t equals the second derivative with respect to time times the tangential component of acceleration plus k times the ds dt squared times the normal component of acceleration, where k is the curvature and ds dt is speed. So find a of t and a of n given r of t equals 2ti plus t squared j plus 1/3 t cubed k. You're like, what is going on? Well, this actually gives you a kind of easy way, we'll see it, to find what a sub t, your tangential and your normal components of acceleration are. So what is r prime of t? 2i plus 2tj plus t squared k. Let's find the second derivative of t. It's just 2j plus 2tk. If we do the dot product here, r prime of t dot r double prime of t, we get 0 plus 4t plus 2t cubed. I need the magnitude of the velocity now to deal with t. So what is the magnitude of the velocity? Well, given that this is the same problem we've done before, we know this ends up being the square root of 4 plus 4t squared plus t to the 4th, which is t squared plus 2. Now, I need to find a of t, I need to take my 4t plus 2t cubed and divide it by that 2 plus t squared, and I'm going to line it up this way just to see what happens. If in the numerator I factored out a 2t, I would be left with 2 plus t squared, so this whole thing is 2t. Now we know to find a sub n, square root of the magnitude of the acceleration squared minus a sub t squared. So what is the magnitude of my acceleration? It's 4 plus 4t squared. Square root of that, but not squared. So this is just 4t squared plus 4 minus 4t squared. 4t squareds cancel, so it's the square root of 4. So the normal component, the acceleration, is 2. And there you have it. And we'll finish this section in the next video.